Hello, and welcome to Vectors Day 2. I am aware that there is another Vectors Day 2 video. However, we have found more time in the school year to teach more material, so that Day 2 video has kind of gotten shoved into Day 1. So you consider this as Vectors Day 2 version 2, if you'd like. So most of the material in the other Vectors 2 video will be part of Day 1, although a little bit of it will be repeated here. However, we're going to start with some new material, including what a unit vector is. Oops, let me go back. Let's see, a unit vector is a vector that has the same direction and slope as another vector, but the length is 1 unit. So essentially everything else is the same, but except the length or that magnitude is short. So let's start with a vector, and we'll call this vector vector v. Oops, that is not a very straight line, is it? There we go. Better. Okay, so let's see. We're going to say that vector v is 3, 4. So let's see, 3, 4, that'll end up about right here. That is my vector v. So the magnitude of vector v here, remember that's going to be the x distance squared plus the y distance squared added together, square root of all that. So in this case, this is the square root of 9 plus 16, square root of 25, also known as 5. So this is just a distance of 5 units here. Well, to find the specific unit vector, we're going to take whatever our vector v is and divide it by its magnitude. So in this case, let's have another vector. Let's call it u. Actually, no, let's call it w. W will be our unit vector here. So we'll have 3, 4 divided by 5, saying that the unit vector here is 3/5 and 4/5. So the unit vector would be to about here, or about 1/5 of the size. Now, the way to double check this would be to take our vector w, we're going to take our vector w and find the magnitude of that. So in this case, taking 3/5 squared and adding that to 4/5 squared and then square rooting that. So if we square all these individually, that's 9 over 25 plus 16 over 25, giving us a square root of 25 over 25, or the square root of 1, which is just 1. So when we find the magnitude of our unit vector, it should just give us 1. Now, something I want to mention briefly that was in the notes of the last video, but not in the last video itself, just because I was kind of hodgepodging things together, is position vectors. Position vectors are vectors just written in a different notation. They're more used when we're dealing with 3D vectors, so when you're getting to multivariable calculus and that type of thing, you'll be using this notation more often. But I just wanted to show you this other notation because we'll kind of start using both of them together. So if I was to have a position vector, it's denoted with 2 variables, I and j. Well, we're dealing with 2 dimensions, so right now just 2 variables, I and j. So if we were to kind of draw in our position vectors here, can never quite draw that in a straight line. Semi better. Okay, so for these position vectors here, let's see, I goes in the x direction and j goes in the y direction. Don't know why I wrote that so huge. But let's see, I itself is in the component form 1, 0, and j is in the component form 0, 1. So when we try to write a position vector, if I was to write a position vector for our vector v above 3, 4, this would look like 3i plus 4j, essentially kind of giving you that x and y value. So again, this is your position vector, just saying that the positioning is at the origin, considered deponent form. So now that we've got that covered, let's move on to direction angle of a vector. And we're actually going to be starting with this vector here. Let me move this up for us. Let's do direction angle of a vector. So as I said, we're going to be starting with this vector we were just dealing with, and we'll do that in our position vector form. So we'll do 3i plus 4j, and I'm saying I want you to find the angle of this vector. So when I graph this out, it'll go to about here, where again, 3 along our x value, this is our 3i, and 4 along our y value, or our 4j. Now, when I'm looking here, I notice I have created a right triangle. And if I'm trying to find the angle here for our value of alpha, I notice that I have my opposite side, I have my adjacent side, I'm looking for the angle. Sounds like I should be using tangent. So overall, we can say that tangent of our angle alpha is equal to our j value over our I value, or really your y over your x, right? Your sine over your cosine. So specifically when we're solving for this one, we're finding tangent of our alpha, it's going to be 4 over 3. And to get alpha by itself, we need to use our inverse on both sides. So we end up with that alpha is about 53.13 degrees. It's not too bad. Now, this is what we're going to do most of the time. However, what if we have something in a different quadrant? That's going to make things slightly harder. So for instance, if we had a different vector, let's say new example, let's say our vector v is now negative 5i plus 4j. So when I graph this, this will actually end up being in quadrant 2. Let's see, negative 5i, 4j, so it's about here. Perfect, so this is now our vector v. So when we go through and we use the material we learned above, and we say that tangent of our angle alpha here, it's the angle we're looking for, is equal to, let's see, 4 over negative 5, our j over our I value. We'll say that alpha is equal to tangent inverse of negative 4 over 5, where the alpha is equal to negative 38.66 degrees. Now this doesn't necessarily make sense for what we're looking at. This is not the answer we want. What's happening here is because of this tangent inverse, our calculator is only giving us a quadrant 4 answer. So it's really giving us this angle right here, which we don't want. We want this angle here. So whenever we are looking for an obtuse angle or an angle larger than 90 degrees, what we're going to have to do is add half of a circle or 180 degrees to find our actual answer. So if we take this negative 38.66 degrees and we add our half a circle 180, we're going to get our actual value of alpha that we're looking for, which is 141.66 0.34 degrees. So this is the real answer of what we need for a direction of, or the direction angle of a vector when the angle is greater than 90 degrees. The very last thing that we will be covering in this video is finding a vector when you have your angle or your direction angle and the magnitude. So again, this is finding a vector, let's call it V, with a direction, which we'll call that angle alpha that we just found, and the magnitude, which again we found in our last video. So let's do an example. So let's say we have the magnitude of vector V is a length of 6. Let's say that alpha is 30 degrees. If we were to draw this out, I don't know exactly where this vector is going to end up, unfortunately, so we're just going to kind of eyeball something. Let's call that vector V. I might give you the drawing of this, but you don't necessarily need it. I would just look for the math of this. So I know that the magnitude here is 6, and I know that this angle here is 30 degrees. Now if we were to look to find this vector, again, I don't know if this is exactly to scale, but please remember that we are looking for this y value here and this x value here. Well, to do that, we're going to need to use our right triangle trig or our SOHCAHTOA. In general, we can say that our vector v is going to be the magnitude of cosine of our angle and also times sine of our angle. So since cosine is our x value and sine is our y value, we can find the values here, but because it's no longer on the unit circle where the radius is 1, we need to use our magnitude here in order to scale this correctly. If you were to do this from scratch, we can do the individual solving here, but you can also just use this equation. So if we were to use the y value here, again, we'd find sine of 30 degrees, which in this case is just our opposite side over our hypotenuse, or y over 6. And then we would, to get y by itself, multiply by 6 on both sides. So that's why we're taking sine of our angle, multiplying it by that magnitude. For people who know the unit circle, we know that sine of 30 is just 1/2. So we end up with a y value of 3, which I actually did draw to scale, totally by accident. Now for the x value, same type of deal. It'd be cosine of 30 is equal to our adjacent side of x over our hypotenuse of 6. So to get x by itself, we're going to multiply both sides by 6 and solve from here. Now again, from our unit circle, we know that cosine of 30 degrees is the square root of 3 over 2. Try to keep this as exact as possible since this is a value that we actually know. So this, once we simplify here, is actually going to be 3 times the square root of 3. So when I write this all together in a single vector, we'll have vector v is equal to 3 times the square root of 3 times 3. So if you have any questions, please let me know. Looking at the completed notes for this video, there's some more examples, but we will make sure to cover that in class. Bye, everyone.